Welcome to our presentation on black holes and the theory of everything. As you can see from the picture, the two characters are trying to solve a mystery. They are doing this by following the footprints and using magnifying glasses. As humans, we would like to solve the mysteries of the universe. How did the universe begin? How did the universe evolve to its present state? And how will it all end? These are the big questions for physics. Black holes are the most mysterious objects in the universe. In this presentation, we will travel on a journey through space and time and explore the nature of black holes, fundamental forces, supersymmetry, hidden dimensions of space, and strings. Our hope is that the journey will lead us to discover the theory of everything. The thinking man is pondering something. We may wonder how the universe evolved to its present state, with so much structure like stars, galaxies, and our own solar system. The answer to many of these questions lies in the Big Bang theory of the universe. There are two main pieces of evidence to support this theory. First, we know that the universe is expanding. Second, we know that the universe is cold. We observe a universe that is large and expanding. Therefore, it is only natural to run the clock backwards in time. If we do so, we are led to the conclusion that the universe was very small and compact at a distant point in the past, almost 14 billion years ago. At that time, the universe exploded in a big bang. The temperature was incredibly high, but as the universe expanded, it cooled down, and structure emerged. Observations today show us that the current temperature of the universe is only 3 degrees above absolute zero. This is called the temperature of the cosmic microwave background. The expanding universe and the cosmic microwave background are remnants of the Big Bang explosion. As we mentioned, black holes are the most mysterious objects in the universe. The force of gravity generated by black holes is so strong that nothing, not even light, can escape. To the outside world, they appear black. However, many mysteries lurk within. It is known that when a large star dies, it will end its life as a black hole. Our goal is to understand these beautiful monsters of the universe. When we explore the universe around us, we are led to the conclusion that there must be a grand design. Although there is incredible diversity in the physical world, we understand that there are only 4 fundamental forces in nature. Firstly, we have the force of gravity. This attractive force is responsible for large-scale structure in the universe and for maintaining the stability of the solar system. The Earth is kept in orbit around the Sun by the force of gravity. Secondly, there is the force of electromagnetism. This is a force between charged particles, such as the proton and electron. It is responsible for the stability of the atom. In addition to these two forces, there are also 2 forces which are active inside the nucleus of an atom. The strong nuclear force is responsible for holding the nucleus together. The weak nuclear force, on the other hand, is responsible for causing particles to decay, leading to the phenomenon of radioactivity. The challenge before us is now clear. We would like to give a unified description of the physical world. This will require a complete understanding of the four fundamental forces of nature. It will also require a complete understanding of how the fundamental particles in the universe experience these forces. We may then ask the question, where does all this take place? The answer is in space and in time. The universe we live in is the playground for the fundamental particles and forces of nature. When we observe the world around us, we are struck by many amazing facts. On the one hand, we see huge structure in the sky, stars, galaxies, and black holes. The size of these structures is enormous, ranging up to 10 to the power of 22 meters. This is called the macroscopic world. On the other hand, we are also aware of small-scale structure in the microscopic world, molecules, atoms, and nuclei. The incredibly small distances involved here can range down to the smallest scale imaginable, 10 to the power of minus 35 meters. You may ask, how can such diversity be unified? Two giants stand out in the history of physics. Isaac Newton, who lived in the 17th century, is responsible for laying the foundations of physics. His deep insight into the nature of mass and force resulted in his laws of motion for material objects. In the 20th century, Albert Einstein revolutionized our understanding of the physical world around us, with his deep insight into the nature of space and time. His theories laid the foundations for modern physics. Our current understanding of the universe would not be possible without the contributions of these two great physicists. Let us begin with Newton. As the story goes, Newton wondered why the apple always fell from the tree. In trying to answer this question, he was led to discover the laws of motion. These laws, called Newton's laws of motion, govern the behavior of all objects in the universe. He introduced the concepts of the mass of an object, the force acting on an object, and showed that objects will only move when acted on by a force. He also discovered the law of gravity. His theory of gravity explained how and why the planets orbit the Sun in the solar system. In the 19th century, Maxwell completed the development of the theory describing the electric and magnetic forces. What he achieved is quite remarkable. In short, he showed how the electric and magnetic forces are really two different manifestations of the same electromagnetic force. However, more spectacularly, he showed that light as we know it is simply one form of electromagnetic radiation. He predicted the existence of electromagnetic waves all traveling at the speed of light. This speed, which is denoted by the letter c, is 300 million meters per second, which is an incredible 670 million miles per hour. At the beginning of the 20th century, much of the physical world was extremely well understood. On the one hand, Newton's laws of motion described the motion of material objects with great accuracy. Newton's law of gravity was also in perfect agreement with experiment. On the other hand, Maxwell's theory of light and the electromagnetic force was also verified by experiment. It came as a complete surprise when Einstein proposed revolutionary ideas in 1905. Through his deep insight into the nature of space and time, he was able to show that Newton's laws of motion required a major revision when objects travel close to the speed of light. Einstein's theory of relativity explained the deep connection between space and time and energy and mass. We have already seen that the playground for the physical world is all of space and all of time. Einstein was able to show that the time elapsed between two events is not absolute. In fact, the time elapsed depends on the speed of the traveller. He also showed that the speed of light is the ultimate speed limit in the universe. Nothing can travel faster than light. One of his most remarkable achievements was to show that mass and energy are equivalent. This new law of physics is stated as E equals mc squared. Having shown that Newton's laws of motion required revision when objects travel close to the speed of light, Einstein then turned his attention to the force of gravity. Newton's law of gravity achieved spectacular success in explaining the orbital structure of the solar system. However, Einstein showed that even light feels the force of gravity. He predicted that light would be bent or deflected by a massive object like the Sun. This prediction was verified soon afterwards. Once again, the laws of Newton required a major revision. Einstein showed how the laws of physics should be modified for high speed and for strong gravity. At the same time, another revolution in physics was underway. This revolution is called the quantum revolution. It became clear at the beginning of the 20th century that Newton's laws of motion were also inadequate for describing physics at very short distances. For example, at distances within the atom. Indeed, combining Newton's laws of motion and Maxwell's theory of electromagnetism led to the conclusion that the hydrogen atom was unstable. Since this is clearly not true, a new theory was developed which correctly describes the motion of particles at very short distances. This theory is known as quantum mechanics. Quantum mechanics led to many new interpretations of the physical world. It showed that particles can also be understood as waves, and waves can be understood as behaving like streams of particles. It also showed that there is a fundamental limit to certain measurements. This is encoded in the uncertainty principle, which states that one cannot simultaneously measure the exact position and momentum of a particle. While quantum mechanics and the theory of electromagnetism were sufficient to explain atomic structure, it became clear that two new fundamental forces were needed to explain nuclear structure. The strong nuclear force is responsible for the stability of the nucleus. The weak nuclear force is responsible for nuclear decay. Modern physics of the 20th century was founded on two pillars. On the one hand, the theory of relativity described physics at high speeds and strong gravity. On the other hand, the theory of quantum mechanics described physics at very short distances. It is amazing, but also expected perhaps, that when we push our theories to the limit, we uncover some deeper truths about how the universe works. Let us turn now to the fact that light is bent by the gravitational force of a very massive object. As we know, we can escape the gravitational attraction of the Earth by launching a rocket with sufficient velocity. This is called the escape velocity. However, we can imagine an object so massive that not even light can escape the pull of gravity. If one compresses enough matter into a small space, then the force of gravity will be so strong that even light cannot escape. It will be bent back towards the massive object. To someone on the outside, this massive object will appear black, since light cannot escape. It is called a black hole. If we take the Earth and compress it into a tiny sphere with a radius of 1 centimeter, then it would become a black hole. If all the mass of the Sun were compressed into a sphere of radius 3 kilometers, it would form a black hole. Einstein's theory of gravity predicts the existence of black holes. Indeed, when a star with a mass more than 3 times that of the Sun collapses under its own weight, it will end its life as a black hole. However, one may ask whether black holes actually exist in our universe. Observations over many years have led to convincing evidence for the existence of numerous black holes scattered throughout the universe. There is strong evidence that a supermassive black hole lies at the center of our own Milky Way galaxy. Its mass is estimated to be about 4 million times larger than our own Sun. The size of this black hole is 7 million miles. In effect, this means that if one travels closer than 7 million miles to the center, one will lose contact with the outside world. One will no longer be able to communicate or send light outside. In effect, one is trapped inside the event horizon. Although the black holes in our universe are incredibly large with a very strong gravity, they hold within them the secrets of the universe. If we wish to understand the structure inside the event horizon, and very close to the center of the black hole, then we must apply the laws of quantum mechanics. In the 1970s, Hawking demonstrated that quantum theory predicts that black holes are not truly black. In fact, they emit energy as electromagnetic radiation at a certain temperature. This is called the Hawking temperature of a black hole. Since Einstein showed that energy is equivalent to mass, this means that the black hole will lose mass and eventually evaporate. This remarkable scenario is called black hole evaporation. In order to put things in perspective, let us consider a stellar black hole whose mass is the same as our Sun. As we have seen, the distance from the center to the event horizon is only 3 kilometers. A black hole of this size has a Hawking temperature of only 60 nanokelvins. This is only 60 billionths of a degree above absolute zero. If such an object were placed in our universe, then it would be colder than the temperature of the cosmic microwave background. Therefore, it would heat up and grow rather than shrink and evaporate. To test our theories of physics, we need to perform experiments and make observations. The experiments, which probe very short distances and very high speeds, require a huge international collaboration among many nations. One such facility is located in Switzerland. It is called CERN. It contains the world's largest particle accelerator. CERN was founded in 1954 and consists of a huge accelerator ring of circumference 27 kilometers, buried 150 meters below the surface of the Earth along the French-Swiss border. Over 80 nations worldwide contribute to this gigantic effort. Fundamental particles are accelerated close to the speed of light and smashed into each other in very high-energy collisions. By studying these collisions, we hope to discover the nature of the universe at very short distances. In this photo, we see an aerial view of CERN. The large white circle indicates the location of the accelerator ring. In the foreground is Geneva Airport, which helps to set the scale. When the particles collide, data must be collected and analyzed. The collisions take place inside huge machines called particle detectors, such as the one shown in this image. Again, the scale of this machine is evident from the size of the workers. Apart from the fundamental physics being explored at CERN, we also see amazing feats of engineering. The equipment needed to perform these high-energy experiments pushes technology to the limit. The theories of Einstein caused a revolution in our notions of space and time. All the predictions of his theories were verified with spectacular success. When particles travel close to the speed of light, they live longer than at rest. This remarkable fact is verified at CERN when unstable subatomic particles are accelerated to high speeds and live long enough to navigate around the accelerator ring. The bending of light by massive objects and the existence of black holes have also been verified. Finally, the expansion of the universe is consistent with Einstein's theory of gravity. Given this remarkable success, we might be led to the false conclusion that all is well. However, history has a way of repeating itself. Although Einstein's theory of gravity predicts the existence of black holes, and is very successful in describing many of their properties, it fails to explain what happens inside the event horizon and at the center of the black hole. Indeed, Einstein's theory fails completely to describe the behavior at the center. This point is called the singularity of the black hole. To understand the physics at the singularity requires yet another revolution in our theories of physics. Our goal is to build a theory of quantum gravity which will describe physics inside the event horizon of a black hole. In order to do this, we believe that we must construct a theory of everything. In other words, we must understand how the fundamental forces of nature are interrelated. The tools at our disposal are the two pillars of 20th century physics: relativity and quantum mechanics. We have almost come full circle. As we know, the universe began in a Big Bang explosion. When the universe expanded and cooled down, structure emerged. Our belief is that there was only one superforce at the moment of the Big Bang. It is only later that the four fundamental forces of gravity, electromagnetism, the strong nuclear force, and the weak nuclear force became manifest. These four forces are the remnants of this one superforce. But what is this superforce? We might expect that a new, revolutionary idea is needed to solve this problem. The revolutionary idea, which is the most promising, is that the universe is made from tiny pieces of string. This idea is a great departure from the ideas of Newton, where the fundamental objects are particles moving as points in space. If the fundamental object is now a string, then it can be either open with two ends or closed with no ends. We must now consider what happens when strings collide, split, and join. When a string vibrates, such as a violin or guitar string, it can produce many different notes. The basic idea of string theory is that the different fundamental particles in nature are simply different vibrations of the same piece of string. Thus, a single string can represent the whole array of subatomic particles. One could say that the music of strings is particle physics. Every theory of physics makes predictions. For the case of relativity and quantum mechanics, these predictions were verified with remarkable precision. When this is the case, we can safely say that the theory is correct and describes the universe we live in. For the case of string theory, the predictions are extremely difficult to verify directly. Two main predictions stand out. First, string theory predicts that the universe has 10 dimensions. In addition to the familiar 3 dimensions of space and 1 dimension of time, there are 6 extra hidden dimensions of space. You may well ask, how can this be? We do not experience any extra dimensions in our daily lives. According to string theory, the 6 extra dimensions must be curled up into a tiny ball, so small that we cannot detect them even with our most powerful measuring devices. Second, string theory predicts that the universe is supersymmetric. What does this mean? We are familiar with many fundamental particles in nature. When we examine their properties, we see both similarity and diversity. Supersymmetry is a special type of symmetry that predicts the existence of a whole new family of fundamental particles, called superpartners. The idea is that each fundamental particle in nature has a superpartner, whose properties are very similar but subtly different. In order for string theory to be a viable theory of everything, supersymmetry must exist in nature. In other words, the universe must be supersymmetric. To test string theory, we need to find evidence of supersymmetry and extra dimensions of space. The natural place to look is in the high-energy collisions taking place at CERN and also at a similar facility called Fermilab in the US. While we must wait patiently for experimental verification, string theory has already passed an important theoretical test. It has successfully explained the structure of black holes inside the event horizon. Since we believe that black holes are the key to the universe, string theory has made great strides in understanding this key. Our final image is of a string and a black hole. Black holes in the universe are large, massive objects with incredibly strong gravity. They remain hidden from view. String theory predicts that the universe is made from tiny pieces of string. Because of their small size, these are also hidden from view. The ultimate goal of physics is to construct the theory of everything. At this point in the 21st century, the most promising candidate for this theory is string theory.